Hello, ladies and gentlemen. I hope everyone is doing well today. Today we are now taking a look at electron configurations. This time, we're going to start learning about the energy of sublevels. So each sublevel has a different amount of energy. An easy way to remember it is the higher the energy level, the higher the energy. So that's what we see right here. So right here we have a list of our energy levels and sublevels. On the left side, we're starting with low energy, and then on the right side, we're going to high energy. It is worth noting, guys, that remember the number in front is the energy level, then the letter that comes after it is the sublevel. So remember, only an S sublevel exists in the first energy level, so that's why there's only one S. Then in the P's, we have 2S and 2P. That's why we only have S and P in the second energy level. Next, in the third, if you're looking at that table from an electron's address, you would have S, P, and D. So that's why we see 3S, 3P, 3D. It is worth noting that it does get a little messed up and it gets a little backwards once we start hitting towards D and F orbitals. The reason why this happens, so this is now, we're next in the next paragraph. So the reason why this happens is because they have ultra high energies. The reason why they have extra high energy is because the D and the F orbital can hold so many more electrons than the S and the P. So it raises the energy. Next, when we're filling in our electrons, there are a few rules that we need to follow. The first one is the Aufbau principle. So this tells us that electrons, they're going to occupy the lowest energy orbitals first. So what that tells us is before we can start filling in any of the electrons in the higher energy, we need to fill in low energy first. So that would mean 1s would have to be full before we can go to 2s. 1s and 2s need to be full before we can go to 2p. 1s, 2s, 2p need to be completely full before we can go to 3s, and so on. The trend continues. Next, so remember, we have that really important fact, I couldn't stress it enough last time, that we can only have 2 electrons in an orbital. This is called the Pauli exclusion principle. And we're going to add to it that they must be spinning in opposite directions. That'll be more important later when we are drawing some more diagrams. But what that means is they're spinning in opposite directions. If we were to have a 1s orbital that has an orbital and we had 2 electrons in it, you would have to put 1 electron spinning clockwise with an upward arrow, and then the next one with a downward arrow spinning counterclockwise. So next, we can use some of this information to answer the first few questions. So question 1, how many electrons would an atom need to have before it can begin filling in the 3s sublevel? So what I'm going to look at is this section right there. So the 1s to 3s. I'm going to write it out right below. That way I don't have to cover it right up the notes. So we need to count the electrons leading up to a 3s before we put the first electron in the 3s sublevel. So remember, each orbital, which are these lines, can hold 2 electrons, and they must be in opposite spins. So we'll put an electron spinning clockwise, and an electron spinning counterclockwise, an upward arrow and a downward arrow. We'll do the same thing in the 2s sublevel. Next we go to 2p. In the 2p sublevel, we do the same thing. We fill in all of the electrons. So now, look at the question. How many electrons would an atom need to have before, so that before is important, before it can begin filling in the 3s? So now the next electron goes into the 3s. So we count them up, because we need to know the electrons before. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our answer is 10 electrons. Next, we can use our periodic table to figure out the element that has 10 electrons. I'm pretty sure I have a periodic table handy. One second, let me go grab one quick. Alright, so now I am back. Well, let's get this out of the center. I'm back with my trusty old periodic table. So remember, we had 10 electrons, so we look for the element that has 10 electrons, the atomic number of 10. So we have neon, Ne. So our answer to 1b is neon. Next, so guys, answer questions 2, and 3 using modeling how I solved 1A and B. So next we have some information that appears in question 4. So in question 4, remember we have orbital diagrams. We call them orbital diagrams when we use arrows. Next, so the one to the right, we'll see that we have little superscripts, little exponents instead of orbitals and arrows. We call this electron configuration. Oh, so remember, little exponents, they are called superscripts. So in 4A, we need to remember, what do the arrows stand for? Remember, they stand for electrons. When it's an upward arrow, it's spinning clockwise. When it's a downward arrow, it's spinning counterclockwise. Next, I want you to think about B and C, but I want you to use this little hint to help you. So when you're answering B and you're trying to figure out what the subscripts stand for, why do you think there are the same number of arrows as the same number as superscripts? Try to think about that, use that to help you. Question 5. So question 5, this starts 5A, B, C, and D. This starts by identifying whether it's an electron configuration or an orbital diagram. Remember, our orbital diagrams have arrows. Our electron configurations have superscripts or exponents. So then next, you need to name the element. Remember, guys, when you're naming the element, the atomic number equals the number of protons, which also equals the number of electrons. So if we were going to name the first one, we can add up all of the electrons. So 2 plus 2 plus 6 plus 2 plus 4, that's 16. So then you'd come over, which element has an atomic number of 16? Oh, it's right in the glare. Right there, my pen's pointing to it, sulfur. So work on the rest, 5A through D. So next we're coming to some information on Hund's rule. So I was going to do this one a little bit backwards. I wanted to help you guys with question 6. Then we're going to look back at the Hund's rule information and work through what this means once we know what Hund's rule is. So in question 6 asking us about Hund's rule. So Hund's rule, the answer is B. Whenever possible, electrons will be unpaired in separate orbitals with parallel spins. So we're going to take a look at the few examples from the notes right now. So what I'm about to say, I already have it written for you in the boxes. I didn't want to highlight everything, so I just highlighted the box. Know that it's important, know that it's there, know that you can find your explanations in the boxes. So the first example, so if we're looking at Hund's rule tells us electrons will be unpaired, so they'll be in separate orbitals. So we can look right here, they're going to be unpaired when possible. So we would look at the 1s orbital and the 2s orbital. It's impossible for them to be unpaired here. So we leave them where they are. Remember, you need to fill in the lower energy before you can fill in the higher energy. What I want to focus on is this 2p orbital right here. So this 2p is wrong because these two electrons, there's extra orbitals for one of these electrons to go into. Remember, they want to be alone when possible. So if we were to rewrite this, we would draw the 2p and we would draw 3 orbitals. Then we would add our electrons. Remember, they want to be separate. So we're not going to draw the electron in the same orbital. We're going to draw it in the next one. We need to look at Hund's rule, though, to remember which direction it's going to spin. It tells us they're going to be parallel spins if possible. So parallel spins, that means spinning the same direction. So if we're fixing this 2p orbital right here, we would draw an arrow, an upward arrow, in a different orbital. So next we can look at Hund's rule again for this example right down here. Again, we need to double check and make sure that all of the electrons are separated if possible, and then when they're separated, are they spinning in the same direction? So we know that the 1s and the 2s are fine. They're going to be full before we can fill in the 2p. But then we look at the 2p and we have 4 electrons, but we still have that empty orbital. So if we wanted to fix this, we would draw our 3 orbitals, and then we would draw our 4 electrons. Remember, they want to be separate when possible with the same spin. So we can start by drawing 1 electron in each orbital. Now remember we had a total of 4, so we have 1 more to add. The one that you're going to add is you can place it in any orbital, spinning the opposite direction. So it will be a downward arrow. So next, if we look at the last example, this last example is correct. The reason why this is correct is because all of the electrons are spread out if possible. The ones that are unpaired are spinning in the same direction. And then the two that are paired up are spinning in opposite directions. So this is how we use Hund rule to make sure we separate our electrons if possible. So, question 7. Question 7, so this is an orbital diagram. This orbital diagram, it breaks Hund's rule. It breaks Hund's rule in the 3p section. I circled it for you. What I want you guys to do is draw that correctly now. Use the models that we have from the information to help you draw it. Next, so the next section we have, question 8. So question 8, we have 3 orbital diagrams, and these ones are all drawn incorrect. We need to fix them. When we fix them, there are 3 rules that we need to remember. So remember on the front, we learned about Pauli exclusion principle, the off-ball principle, and then we just learned about Hund's rule on the top. So we need to analyze each of these electron configurations for each of these rules to see if it's breaking them. So the first example is we can take a look and see if this follows the Pauli exclusion principle. So remember guys, Pauli exclusion principle is only 2 electrons can fit in each orbital. So we can double check. Is there at least 2 electrons in each orbital that they need to be in? So we can look, there's 2 in the 1s, there's 2 in the 2s, 2 in each orbital in the 6p. We're missing 1 in the 3s, and then we still have a couple in the 3p. So what we need to focus on is what's going on right here. There's something weird going on. We don't have the 3s orbital is not full before we go to the 3p orbital. So this one kind of breaks 2 rules. It breaks the Pauli exclusion principle because this 3s orbital would want to be paired up with another electron if it can be. And it can be because we have electrons in the 3p orbital. It also breaks the off-ball principle. So remember guys, the off-ball principle is found on the front. Electrons, they want to be in the lowest energy orbital possible. So these electrons, so this electron would want to be over here before it would want to be over here in the 3s sublevel before it was ever in the 3p sublevel. So we just need to redraw this correctly. So we know that we would be in 3s. We would have our 1 orbital. We would have to have 2 electrons in there before we went to 3p. And then in our 3p orbital, we would only have 1 electron left. So we would have an upward arrow. So now what I want you guys to do, analyze the electron configurations. Remember, look at the electrons. Remember, look at the energy levels. Make sure they're going in the correct order. And then when you find what's wrong, correct it. Make it right. Next, question 9. So question 9, now we're going to be translating electron configurations into orbital diagrams. So remember guys, the difference between them is what we find right over here. So remember guys, the arrows become the exponents. So these can be pretty easy to transfer. Or sorry, the exponents, in this case we're going from electron configurations to orbitals. So in this case, the superscripts, the exponents, become our arrows. So we would have 1s. So we would write 1s. We would need to remember that there's one orbital in the 1s energy level. So then remember, if you need to remember how many orbitals are in each energy level, you can look that up on table 2 in an electrons address. So then there's 2 electrons. So we would do 1, 2. Then we do the same thing for 2s. Look it up on table 2 and you see that there's 1 orbital. We have an exponent of 2, so that means we have 2 electrons. Remember, make sure they spin in opposite directions, so an upwards arrow and a downward arrow. Next, we have 2p. According to table 2, there are 3 orbitals. So this time we have 6 electrons to work with. And that makes sense because if you have 2 electrons per orbital, it would be 2, 4, 6. So again, we do the same thing, making sure they spin in opposite directions. So an upwards arrow and a downwards arrow. After 2p comes 3s. So we use our 3s. Again, there's one orbital in s's. So we put our 2 electrons, which we see right here, 2 because the exponent, an upward arrow and a downward arrow. And then lastly, we are now in the 3p. This time though, it's worth checking out and remembering, or focusing, because we have an exponent of 2. What that tells us is we only have 2 electrons in this 3p sublevel. So we need to remember to follow Hund's rule. Remember, Hund's rule tells us they will be unpaired in separate orbitals with parallel spins, so spinning in the same direction. So we pick 2 orbitals and we put an upward arrow in each of them. So now what I want you guys to do, I want you guys to do B and C, translate your electron configurations into orbital diagrams. Question 10a. Question 10a, you need to figure out the elements that you find throughout 9a, b, and c. So remember guys, the atomic number equals the protons and the electrons, so we can use our periodic table to do this. So remember, you can count up the electrons, and then you can use that for your atomic number to find it on the periodic table. So watch, I'll do 10a with you. So we count up the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So then we come look at our periodic table. We find atomic number 14, and we see that it's silicon. So then our answer, silicon. So do the same thing for 10b and c. Next we're going to draw electron configurations. So to draw electron configurations, we need a few things. Or write them, draw them, whatever you want to call it. We need this list of energy levels, going from low energy to high energy. So how we have to solve this. So the first one I have written out, and then I will solve 11b, and then you guys can do 11c and d. So we look up phosphorus on the periodic table. We see that phosphorus has 15 electrons. So we know that our electron configuration needs to have 15 electrons. So essentially what you're doing is you are using this list of energy levels on the top of the page, this list of energy levels, and then you're just filling in electrons until you have 15. So I like to cross off the electrons so that I can visually see them being used up, and then I remember when I need to stop. So we start with 1s. You can have 2 electrons in an s orbital, so we write the exponent of a 2. And then we cross off 15, we have 13 left. We do the same thing for 2s, because 2s comes next. S orbitals can hold 2, so we would write the exponent of the 2, cross off the 13, we have 11 left. We next do the same thing, we look at our list, 2p comes after, so then p orbitals can hold 6 electrons, so we write a 6, and then we cross off our 11 and subtract 6, so we have 5 left. Next, after 2p comes 3s. So we write our 3s, and then remember s orbitals can hold 2 electrons, so we write a 2. We subtract, we have 3 left. Then after 3s comes 3p. So in 3p, we can hold a total of 6, but we only have 3 left. So that's why the exponent is a 3. Remember, at the end, you're only going to use as many electrons as you have. So we would write the 3, and then we have 0 left. So right now, guys, we can do this for neon. Remember, neon's not done for you, so make sure you take down these notes. Try to model 11c and 11d the same way. So we look up neon on our periodic table right here. It has an atomic number of 10. Oh, it's a race. Who can finish first? My battery power or me? So then we have neon with 10 electrons. So we start the same way. We look at what comes first in our electron configurations, 1s. So we write 1s. Remember, s orbitals can only hold 2 electrons. So we write a 2. We now have 8 left. After 1s comes 2s according to our list. So we write 2s. Our exponent for s orbitals are 2. They can only hold 2 electrons. So we would cross off our 8 and write a 6. After 2s comes 2p. So we would write 2p. Remember, p orbitals can hold 6 electrons. So we would write a 6. Oh, and that works out perfectly because now we have no electrons left over. So this is our electron configuration for neon. So do the same thing for 11C and 11D. So next question 12. So question 12, use the following electron configurations are incorrect. You need to fix them. So this little note in the margin, ignore it. That's not going to help you. So what you guys need to do is you need to look and see how they're configured. So this electron configuration has a total of 2, 4, 6, 8 electrons. And then we also need to check and see, look at our energy levels. Are they in the correct order? Remember, they need to go from low energy to high energy. So if we look at our energy levels, it would go 1s. Oh, yeah, you can see it. It would go 1s, 2s, 2p, then 3s. Is that what we see down here? Down here, it goes 1s, 2s, 3s. So right here, right where I circled, we're missing 2p. So we need to draw this correctly with 8 electrons. So then what we would do is we would do the 1s orbital comes first. We have an exponent of a 2 because it's a little difficult now because the page is long, so I can't really hold the orbital diagrams underneath it. Can I? So we would look and we would see it goes 1s. So then 1s in our list right down here. Then it goes 2s, 2s in our list, then 2p. Remember, s orbitals can hold 2 electrons, so that's why we go 2 in the 1s, and then there's 2 in the 2s. And then lastly, we would have 4 left over, so we put 4 in the p orbital. So I would like you guys to do the same thing for 12A, B, C, and D. Next, question 13. So question 13 is using nitrogen's orbital diagram, which is drawn for you. So nitrogen has 3 unpaired electrons and 4 paired electrons. So remember guys, paired electrons, you have 2 electrons in the same orbital. So that's what you see right here. 1s and 2s have the paired electrons, and then 2p has the unpaired electrons. So think about what unpaired means, and then relate it to unpaired electron. How are the electrons in the 2p orbital different than the electrons in the 1s and the 2s? So guys, when you do question 14, so question 14, you need to figure out the number of unpaired electrons in oxygen. So to solve number 14, what I want you guys to do is draw an orbital diagram for oxygen. Then you can look just like nitrogen and see which electrons are unpaired. And ask yourself, how many electrons are alone? Alright guys, if you have any questions, please make sure you circle them and write down what you got stuck on, what you need help with. Like always, I'll try to end these with a joke. So what do you call an alligator in a vest? An investigator. I hope everyone has a wonderful day. I will see you guys in class. Bye.